Alright, let's do a series on Fourier series, and then we will eventually move on to Fourier transform, and then we'll try to do, let's see how things work out. So here's the thing. What is Fourier series? Fourier series allow me to actually convert a signal which I have either a periodic signal or an aperiodic signal into frequency component. Alright, so let's say if I have a signal like this, the signal is repeating itself after some period. So t is the period. The signal is given f of t. As after some period is going to be f of t plus n times t. It's repeating itself after period. So this is an example of a periodic signal. All right. And let's say I have a signal like this. Let's say I have some type of a signal like this. Now, it's hard for me to visualize this signal in time domain. If I were to look at it in terms of an oscilloscope, this would be very hard for me to actually visualize this. So Fourier allow me to actually look at an individual frequency component of this particular signal. Right? So if I were to see this on an oscilloscope, I would see a garbage like this. But when I look at the same signal on a spectrum analyzer, then I might see an individual component, individual frequency component, which are present in this complex looking signal. So the first step in order for me to do that, so what a spectrum analyzer does is actually we're going to use Fourier series, and then eventually we'll move on to Fourier transform. So this is how you're going to apply Fourier series. There's a condition which is known as Dirichlet condition. After some German mathematician that says if my signal is if the sum of f of t is less than infinity, basically what that means that my signal is finite. If I have a signal that is finite, if I have this particular function, I'm just keep saying it, signal function, same thing. If I have a function that is finite, then I can definitely decompose that into Fourier series, which means I can look at its sinusoidal components. All right. If I have a function that is finite according to Dirichlet condition, which means that I can decompose this particular function into sine and cosine terms. So we're going to look at a couple of different formats. So we're going to look at format number 1 of Fourier series, and then we're going to look at different formats of Fourier series. All right, so here's what it is. So the Fourier series, the definition of Fourier series is this. So I'm just going to write this. So Fourier series, f of t is given as a naught. All right, so I'm just giving you a definition of Fourier series. You have summation symbol where n is going from 1 to infinity. All right, we have an cos 2 pi n f naught t plus bn sine 2 pi n f naught t. All right, so this is the definition. So if I have a function that is finite, I can break this down into Fourier series, which means I can look at a periodic, sinusoidal or cosinusoidal component of this particular signal. So here's the definition. Where do I have a naught, which is going to be your DC component? All right, so a naught is always going to be your DC component. So whenever you look at a signal, the first peak or the first individual peak, so let's say it's like this. So let's say this is a Fourier transform of something. This, the first fundamental peak that you would see, that is actually your DC component, which is a naught. All right, where you have, okay, n is just number of this period, or how many times this period has occurred. That's what n is. It could be in positive integers value, starting from 0 to positive 1, 2, 3, and all the way up to positive infinity. F is the frequency, 1 over t. Summation. So basically what am I saying is this function, it has some DC component, and this function, it's actually a summation of a cosine and sine. I hope you're getting it. When it fulfills the Dirichlet condition, which means you can break this down into Fourier components, which means you can actually look at sinusoidal and cosinusoidal components. So basically what this function is saying is that this thing will have some DC component, and it actually will comprises of some type of a sinusoidal component and cosinusoidal component. All right, n is just referring to number of harmonics. Is it a first fundamental component, second fundamental, third, fourth, fifth? F is just referring to frequency. All right, so a naught can be defined as 1 over t, and you're gonna integrate it with respect to the period, f of t dt. Right, this is one of the definitions that which is most commonly seen in textbooks. Then we also have an component, which is this guy. This is defined as to be two of t. You're gonna take that integration with respect to t, f of t cos 2 pi n f naught t dt. So this is going to be your an component. This is your DC component. This is your an component, and this is your bn component. Bn, let's define bn over here. Bn is going to be 2 over t. You're integrating with respect to the time period, f of t sine 2 pi n f naught t dt. All right, these are the three components that we need to find if I want to find out how what this signal looks like in terms of frequency domain. So Fourier allows me to see a signal which is in time domain. I can easily look at that signal into frequency domain, and once I look at a signal in frequency domain, I'll have a better picture of what my signal look like. So this is how we actually find these values out, where n, sorry, not from 0, is actually from 1. N is from 1, 2, 3, 4, 5, 6, 7, and all the way up to positive integers. So this is a one way of looking at it. One way of looking at it. In this way, we can also look at Fourier. So let's just call it form number 1. This is one way of looking at Fourier series. All right, so let's look at another form of Fourier series. All right, I'm just going to write it down here. Same thing, just like you see it over here. Just like you see it over here, I'm going to write this initial format down, which is going to be a naught plus summation n goes from 1 to infinity an cos 2 pi n f naught t plus bn sine 2 pi n f naught t. All right, this is an actual form. Now when I look at something like this, I can apply my trig identity here. My favorite trig identity is this: a cos of alpha plus b sine of alpha that should give me a squared plus b squared cos alpha plus a tan negative b over a negative b over a. All right. So I can use this trig identity and apply it in place of this. So we can come up with another form of Fourier series in which I can do that. So let's apply this over here. So we have a naught as is. All right. We have our summation that is going from 1 all the way up to infinity. All right. So what is my what are the values of my a and b's? A's and b's are going to be my an and bn. So an is just going to be an squared. This is where that squared is coming from, plus bn squared. Whole thing is under root. All right, whole thing under root cos. What is my alpha? Alpha is 2 pi n. All right, alpha is 2 pi n f0t. All right, minus, sorry, this is a tan. All right, arctan minus sorry, plus. There's a plus sign here. All right, there's a plus sign in that trig identity, and then this negative when it goes out, so that's become negative. So this is going to be negative a tan. And what is going to be my b? My b is bn divided by an, and this is another format. So let me write this down. Let me write this down again. So this can be rewritten as, so a naught can be replaced with c naught, cn can be replaced with an squared plus bn squared. All right, and theta n can be replaced with negative a tan bn divided by an. All right, so the third format, it might look something like this, and this is known as complex form. So my output, which means the other, so the out, I mean the form, second form, which might look something like this. So the end result of my Fourier would look something like this. Hold on. So the second form would look something like this. C naught plus summation n from 1 to infinity. All right, in place of this whole thing, I'm gonna write my cn. I'm gonna write my cos function, cn cos, which is going to be 2 pi n f naught t, and in place of this, I'm just gonna simply write theta n, and boom, this is Fourier series in complex form. All right, so first form is this. Second form, what I have done is this, exactly the same thing. I've written that down. I use my trig identity a cos alpha plus b sine alpha, that is equals to a squared plus b squared under root cos alpha plus arctan a tan, so this is arctan, times negative b over a. I have just simply applied this on this identity on these terms. Okay, so I have a naught, let's just leave it as is for right now, an squared plus bn squared, which is this, I'm calling it cn, cos alpha, which is 2 pi n f naught 0 t, a tan, bn is this guy, and which is b, and an, which is this guy, is an. So minus a tan bn over an, I'm just calling it theta n, right? And Cn, I'm calling this whole thing Cn. So this has become this. So this is actually a complex form of Fourier series, right? So first form is this, second form is this. I think this video is getting too big. So if you have any questions regarding what we have done right now, leave it in a comment section, and don't forget to subscribe to my channel.